this video, we're going to take a look at Charles's law. This is very similar to Boyle's law that we previously saw, except we're looking at the relationship between volume and temperature. And volume and temperature have a relationship that is different than volume and pressure, right? So let's take a look at what that relationship is. So if you have a particular gas, like you see here, and the pressure is constant, what would change about the volume if I change the temperature, right? So what I'm going to do here is I'm going to increase the temperature. Right now, temperature is 260 Kelvin and the volume is 481 liters. So if I increase the temperature, I notice that the volume is increasing as well. Well, what if I decrease the temperature? If I decrease the temperature, the volume is also decreasing, right? So this shows or represents Charles's law, which summarizes that volume and temperature have a proportional relationship, which means I can represent it like this. So volume, So when volume increases, temperature increases as well. And this can be further summarized by Charles's law, which is the formula which states that if you know V1, T1 is equal to V2 over T2, right? This formula represents the relationship between volume and temperature. So if you know the initial volume and the initial temperature, you can figure out the final volume and the final temperature, right? You need any three of these variables and you can figure out what the fourth variable is by doing your calculation. Now you'll see this formula expressed also in this way, which is V1 times T2 is equal to V2 times T1. Now this is the exact same formula, just rearranged in a different way. If you use either one, you'd still get the same answer. Now let's see why this occurs. Why is it that when you increase temperature, volume increases as well? Well, when you increase temperature, the particles have more kinetic energy, right? The gas particles move faster. And because they move faster, they have more collisions and the container expands. Whereas if you decrease temperature, the particles have less kinetic energy, which means that they're moving more slowly, which results in fewer collisions, which then decreases the size of the container. So let's take a look at some calculation problems to solve using Charles's law. Just like we did in our video with Boyle's law, we're going to write down all of our variables, and that's going to help us identify what we're solving for. So in this question, they're saying that the balloon is inflated in a room, which the temperature of the air is 295 Kelvin. So the initial temperature is 295 Kelvin, and the balloon has a volume of 650.0 milliliters. The balloon is put into a refrigerator at 277 Kelvin and left long enough for the air in the balloon to reach the same temperature as the air in the refrigerator. So we know that there has been a change in temperature, and T2 is 277 Kelvin. What they're asking us to do is predict the volume of the balloon, assuming that the amount of the air has not changed and the air pressure in the room and the refrigerator are the same. So the pressure remains constant and the amount of gas remains constant, and we have to solve for V2. So knowing our formula, which is V1 over T1 is equal to V2 over T2, I need to rearrange such that I am solving for V2. So V2 should be the only thing on this side of the equal sign. So I have to move T2 over to the other side. Right now it's being divided. So if I take it over to the other side, it's going to be multiplied. So I'm going to have V1 times T2 divided by T1 to get me V2. Now let me just sub in my numbers. So volume is 650.0 milliliters times T2, which is 277 Kelvin, divided by 295 Kelvin. This gives me V2. Now my kelvins do cancel out. Now it is very important for us to remember that if we are using Charles's law, our temperature has to be in Kelvin. So if you were given in this question degrees Celsius, you have to use our conversion to convert into Kelvin and then use our formula. Okay, so when I set this into my calculator, I have 610 milliliters. I'm gonna put a decimal place there to show that there are 3 sig figs. So this is 4 sig figs, this is 3, this is 3. The lowest number of sig figs in the question is the number of sig figs in my answer. So 610, that's supposed to be a little decimal place there. Now, you might be wondering, why is it that I know that this is in milliliters? Well, when my units of Kelvin canceled out, the only unit that I have left over is milliliters, so my V2 is also going to be in milliliters. Now, had this been liters, that's totally fine. That would just mean that my final answer is also going to be in liters. Let's take a look at another example. If you want, you can pause this video and unpause it just to take up this answer. Right, so in this question, a birthday balloon is filled to a volume of 1.50 liters of helium gas in an air-conditioned room at 294 Kelvin. So I am given initial volume, 1.50 liters, and I'm also given initial temperature, which is 294 Kelvin. The balloon is then taken outdoors on a warm, sunny day and left out as decoration. The volume of the balloon expands to 1.55 liters. So I know that there has been a change in volume. So V2 is equal to 1.55 liters. Assuming that the pressure and the amount of gas remain constant, what is the air temperature outdoors in Kelvin? So they're asking us, what is T2? What is the second temperature? Again, I'm going to go back to my formula. This time I'm just going to use the other the way that it's arranged. Again, it doesn't matter. It's the same formula. When you rearrange to find T2, you're still going to get the same answer, right? So I'm going to first rearrange. So T2 is equal to, I need to get rid of V1. I have to move it over to the other side. Right now it's being multiplied. When I take it over to the other side, it's going to be divided. So V2 times T1 divided by V1. V2 is equal to 1.55 liters. T1 is equal to 294 Kelvin divided by V1, which is 1.50 liters. Now, what this does, when I have this formula, all these numbers plugged in, my liters will cancel out, and what I have left over is Kelvin. Now, if this was in milliliters, right, that's totally fine. My milliliters would cancel out. What I cannot have is V1 and V2 in 2 different units. If one of these was milliliters and the other was liters, I just have to convert one to make sure that they're both consistent. Okay, so when I type this into my calculator, I am going to get 304 Kelvin, right? All 3 of these numbers have 3 significant digits, which means my final answer will also have 3 significant digits.